Okay, good morning. So I saw, first I saw that many of you are not here. I wrote a problem. So if you want, you can write this problem in your notebook or something. But I will make a video to solve this problem. It's a very nice problem. You have to be creative. The algebra is not complicated, but you have to be creative in order to be able to solve. So now that you are here, so let me just forget about it and start today's lesson so that we can complete everything that I want to cover. Okay, so here a, b, and c, and d are real numbers. We know that a plus bi to power 5 is c plus di. We want to show that it is possible just simply switch a and b here, c and d here, which is not very natural to do. But for this case, this happens to be true. Okay, so I will solve that later. Okay. So today I want to talk about the complex plane. This is a very important topic. And it doesn't mean it is hard, but it is important to understand what is going on here. Because you know that so far, a complex number is an abstract notion. It's just a number. Yes, we don't have any imagination, something about the complex number in our head. Usually, human brains are well adapted to consider shapes, figures, something like that. So, not make it so abstract. And according to this, mathematicians have developed the notion of the complex plane. The notion of the complex plane is essentially the same as the Cartesian plane, I mean the system of coordinate systems, but we change the names. So the horizontal axis, instead of being called the x-axis, it is called the real axis. And the vertical axis, instead of being called the y-axis, it is called the imaginary axis. And of course, they are, as before, perpendicular, and this intersection point is called the origin. So all the properties you had for the normal coordinate system, you have it here. But the only thing is that, how can I represent a complex number like a plus bi? So a complex number is an abstract notion. It is a number. It just lives in your head as a number, yes? But now, according to this setup, if I find the real part on the real axis, so let us say this is A, and if I find the imaginary part on the imaginary axis B, and then find that point, this point is Z, okay? So that's it. So from now on, we have two things to think about a complex number. One is just an abstract number that lives in your imagination. Secondly, if you want to have something more tangible, you can visualize it as a point on the complex plane, whose x-coordinate, as before, is the real part, and the y-coordinate, of course, is the imaginary part. That's it. Is that clear? For example, I can ask you to represent these numbers. So let us write z1 to be 2 plus 3i. Okay, so where is it? I have my setup here. The only difference is that this is not called the x-axis, it is called the real axis, and this is called the imaginary axis. If I want to represent this, I have 2 here, and I have 3 here. And then this will give me this point. Yes, 2 and 3. This is the point corresponding to that complex number on the complex plane. Okay, for example, what is this one? Z2 equals to minus 2 plus I. So this means that the real part is minus 2, the imaginary part is 1. Yes, so it means that, for example, I go here, minus 1, minus 2, and the imaginary part is 1 unit. So this point that you see here is point Z2. Okay, for example, what is Z3 to be just 1? The imaginary part is 0, so this is nothing except Z3. And then I don't know, for example, what is Z4 equals to minus 2i? It means the real part is 0, the imaginary part is minus 2 units, so this becomes that point. This is Z4. Yes? So this is one way to visualize an abstract complex number using some kind of pictures or figures. Okay, this will help us to somehow understand the properties, algebraic properties of complex numbers using geometrical properties of points and lines and things like that. So we can find a connection between algebra and geometry. Sometimes some problems are simpler to solve algebraically. Sometimes, if we can have a good interpretation of geometrical picture of the complex number using our geometrical intuition might help us to solve the problem simpler. I want you to understand, and we'll see some examples of this. Some of them might be a little bit hard, but it is not that hard. Another perspective is instead of denoting representing a point, representing a complex number by a point, sometimes we represent a complex number by a vector. And the vector is the one drawn always from the origin pointing to that point. Yes, for example, this complex number, you can denote it by a point if you want. Both perspectives are actually important. Sometimes you denote it by a vector, but if you want to denote it, if you want to represent it by a vector, that vector should start from the origin always and end at that point. So this point is this complex number is denoted by a point, represented by a point or a vector. For example, I don't know, this can be represented by this point and also this vector. This one can be also represented by that vector. This one can also be represented by that vector. Yes? Is that clear? So that's the very simple idea of complex numbers on the plane. So now let me ask you some questions to understand this concept a little bit better. For example, if I give you a complex number, from now on you have two methods to visualize it. Abstractly, like numbers, geometrically, like points or vectors. Okay? So let us say that I pick a random complex number in my head. I don't tell you what that number is, but I multiply that number in my head by minus z. It becomes a new complex number. This complex number is represented by a point. This is also a new complex number, so this should also be represented by a point. My question is that, do you think there is any relation between the points representing these two complex numbers on the complex plane? What is that? How is the relation? Is the question clear? So for example, this is z1, 2 plus 3i. Now let me multiply z1 by minus sign. It becomes minus 2 minus 3i. And if I ask you find this point, you go minus 2 and minus 3i, yes? This is minus z1. This was z1. How z1 and minus z1 in general connected? Yes?
They're the opposite or mirror
Image with respect?
to both axes.
Both axes is correct, but we can say the origin. Yes? So it means that if I connect this point, my picture is awful, of course, but if I connect this to the origin and continue it as much as I have so far, I will reach to minus z1. So a complex number z and its negative or its opposite are symmetric with respect to the origin of the complex plane. So this is one question. What do you think will happen for z and z bar? How they are connected? If you know the point z on the complex plane, where is z bar? Geometrically, of course, you can always calculate and find. That is not the point. I want you to learn, without calculating it algebraically, guess where z bar is. Yes? Yes, it is flipped over the x-axis. Yes? Why? Because when I told you that z is a plus bi, when I say z bar, what do I mean? I mean I keep the real part the same. I change the sign of the imaginary part to the opposite. So it means that the real part is not affected, but the imaginary part is opposite now. So it means that if this point is here, z bar is exactly here. And I don't know if this point here, z bar is there. So it will be flipped with respect to the x-axis or the horizontal axis. Yes, is that clear? Okay, so remember these are important things, okay? So if I have a complex number, what happens if I multiply it by minus sign? If I have a complex number, what happens if I conjugate it? For example, can you understand this rule that z bar is z? Using geometry, not algebra. Because when I take z bar, if I have a point, when I take bar, I flip it with respect to the horizontal axis, and then I take the z bar again, I flip it with respect to the x-axis, I return back to the original point. So this is a geometrical understanding of why z bar is equal to z. Yes? So this is good to have both pictures in mind. So here, in this case, so far we learned about algebra, how to manipulate complex numbers at the level of arithmetic and algebra, but now we want to understand the connection between this and the geometrical picture. Okay, a little bit harder question is that, what happens if I have a complex number, I just multiply it by I. If you have a complex number, it is represented by a point. If you multiply that complex number by I, it becomes a new complex number. That new complex number is also represented by a new point. My question is that how these 2 points are related, the original point and the new point.
The angle, when you add up the angle from the real plane, you get 90 degrees on both.
So what is the name of this kind of operation? So what is happening if you want to write it in, if you want to express it in mathematical terms? So for example, what you're saying is correct. So for example, let us say that I have z equals to a plus bi. Okay, so let us say that this length is a, this length is b, just to visualize. So that point is point z. Okay, now my question is that what happens if I multiply it by I? This becomes I a, this becomes minus b, because I squared is this. But when I want to write it in a standard form, I write the real part first, then I would write the imaginary. So now if I ask you to represent this point, where that point is, that point has a real part minus b. This length is b, so this length becomes minus b. Do you agree? Because minus b has the same length as b, but now this is the real part. It was already the imaginary part. So this is minus b, and where is ai? So a is this length, yes? So now this is this length. This is a. Is that understandable? So that's the imaginary part. So now the new point is this point. So if I ask you if this is z, what is the name of this point? The name of this point is iz. Now, what Samuel said is true. This point, if you rotate this point about the origin 90 degrees, my claim is that you end up with this point. Yes? Why? Because, for example, if I draw this line from here to here, and I draw this line from here to here. So first of all, what is the direction of rotation? If it is really rotation, it should be counterclockwise. Counterclockwise in mathematics is by convention the positive rotation. Okay, so you see it was z, now it is iz, but I haven't proven yet this is indeed a rotation. To prove that this is indeed a rotation, I need to show that the length of this blue line and the length of this blue line are equal. Yes, because then it means that I have rotated this, yes? Is that right? So why this length and that length are equal? It's very simple, because this triangle that you see here is congruent to this triangle that you see here. Why? Because this length by construction was equal to this length, and which is equal to that length. And this length is equal to this, by construction is equal to this. So these two triangles are congruent. If they are congruent, the hypotenuse of one of them is equal to the hypotenuse of the other one. But what about this angle? So Samir mentioned that this angle is 90 degrees. But why is that? Why that angle is 90? So far I have shown it is rotation. But the point is that the angle of rotation is this much, and we are claiming that this angle is 90. Why is that? Yes? No, from geometrical point of view. It's not that hard. You see, for example, what is this angle plus this angle? What is that? This is 90 degrees, because this is a right angle triangle. But because this triangle is congruent to this triangle, this angle is also equal to this angle. Yes? This angle plus that is 90. This is equal to this one, so this and that in total is 90. And the whole thing is 180. So what is left for us? 90 degrees. So remember this. It's a good thing to remember. If you have a complex number and you multiply it by I, what happens to the point? The point is being rotated counterclockwise about the origin. How much? 90 degrees. It's good to have this in your memory. Okay, let me ask you another question. What happens if I multiply my complex number by minus I? So forget about IZ. I take this one again, but instead of multiplying by I, this time I multiply by minus I. What will happen to the point? Yes?
They will rotate clockwise or negative.
Clockwise, that is correct. So instead of rotating anti-clockwise, you rotate clockwise. Okay, can you say why? Of course, you can start this from scratch and use this algebraic method to convince yourself. But don't do that. Try to use what you have learned so far to justify what Melvin said is true, or you yourself if you want to. How can I visualize minus I times z as a combination of the previous operations we talked about? So you need to see it in this way. If I want to go from z to minus iz, what I do first, for example, I multiply by I first, and then I get a new number. I forget about the original one, take this and multiply this by minus sign. I get to the new one. So if I want to go from here to here, I did it in two steps. First, I multiplied by I, then I multiplied by minus 1, or a minus sign. So what happens? When I multiply it by I, it is rotated and it goes up to here. Now this is my new point. I multiply this new point by a minus sign to reach to this, what I want to. But we learned what is the effect of multiplying a complex number by a minus sign. It will be flipped about the origin. Yes? So this is what you said is correct, because if I go here and flip it here, then of course it will be rotation on this direction. Yes? But this imagination I want you to have. It's not hard. One of the interesting things, one of the technique students told, he told me that, okay, instead of minus iz, he did it, of course, like this. He multiplied by I, he got iz. He multiplied again by I. What does you get? You get I squared z, but I squared z is minus z. And then you multiply by I again, you get minus iz. I'm not saying this is the optimal way, but this is possible. And let us see what happens. Whenever you multiply by I, you are supposed to rotate 90 degrees about the origin clockwise, anti-clockwise. So you multiply this by I, you reach here. But now this is your new point. You multiply by another point, I, what is supposed to be done? This should be rotated 90 degrees, counterclockwise again. And then if you multiply by another I, this point will be rotated counterclockwise 90 degrees. So in total, how many degrees you have rotated your original point? 270 degrees about the origin. And of course, it will be clear, this is the same as rotating in this direction minus 90 degrees. Yes? Is that clear? So these kinds of arguments are good to know about. What happens Of course, this is not very simple. For example, if I ask you, I have a complex number, where is 1 over z? These transformations have been studied, but they are harder. So for example, if I show you this is the point z, show me where is 1 over z. It is not that easy, but you can do it, okay? Later probably we will be able to discuss about this, but not right now. Any questions? Okay. So now this vector picture is also important to realize. One important thing. Now, do you remember we talked about absolute value of a complex number as a number? But in geometry, what is that absolute value? What is the meaning, geometrical meaning of the absolute value of a complex number? So let us say that I have a complex number. Do you remember what was it, for example, like this? And when I ask you what is the absolute value of the complex number, you will tell me it's square root of a squared plus b squared. This is a number, this is algebra. But now, at the level of geometry, what is the geometrical meaning of absolute value of a complex number? Anyone else? Yes?
It's the length of a triangle, the hypotenuse of a right angle triangle with the sides A and B.
Yes, that's correct. Another
Magnitude of the vector.
magnitude of the vector again?
The length of the vector.
Yes, you are talking about vectors. But talk about the point perspective. What's the, yes?
This is
The distance from that point to the origin. Yes? So when I say the absolute value z, so if I have this scenario, let us say this is A, this is B, and then what happens, this is the point z, and from here to here is what? From here to here, this length is b, this length is a, so this length is the square root of a squared plus b squared, which is equal to absolute value of z. So remember this picture in mind. So if you have a complex number, the distance from that point to the origin, or equivalently, the length of the vector representing that point is given by the absolute value of the complex number. So that's important to understand. Okay, before continuing, let us work a little bit on absolute value. So I give you 2 points, z and w, on the complex plane, and then I subtract them, and then take the absolute value. Okay, now my question is that, can you interpret this number geometrically? What is the interpretation of this absolute value geometrically? I give you 2 complex numbers. These are numbers, but you can visualize them as points. So now you have 2 points. Now my question is that if you calculate the absolute value of z minus w, it becomes a number. What does this number represent on the complex plane? Anyone else? Yes? Yeah, yeah, yes. Yusuf. Do you want to say? No? Melvin?
It's the distance from the origin to the point z minus.
This is one explanation. It's not a good one. It's correct. Because you told me the absolute value of a complex number means the distance from that point to the origin. Now the only thing that you are saying is that z minus w is a complex number, is playing the role of the original z. So it means that this is the distance from this complex number to the origin. It's not wrong, it's correct, but I don't like it because we can interpret it in more natural ways. Yes? Yeah?
point of the difference between those numbers. This
No, there is a very, very fluent English sentence saying that. It measures the distance from z to w. It's more natural to say that this is the distance from z minus w to the origin. Yes? It is better to express it in terms of z and w rather than bringing origin in and then compare the distance from z minus w to the origin, which of course was true. But why is that? For example, let me write z equals to a plus bi. This is very important. I would write it as a remark there. So c, and then let me consider w to be c plus di. And then I want to calculate this algebraically. What is that? So I need to calculate z minus w first. This means a plus bi minus c plus di. But we know that this becomes a plus bi, minus sign goes in, it becomes minus c minus di. I collect them in a standard form, I take a minus c together, I factor an I out, b minus di together. And now, I ask you, what is the absolute value of z minus w? So do you remember? The absolute value of any complex number is the square root of the real part squared plus the imaginary part squared. So this is exactly the absolute value of z minus w. But let me try to interpret this. This is the distance formula. Do you remember in Math 2C? So if I want to, for example, understand what is going on, let me, for example, this is the real axis and this is the imaginary axis. So for example, let us say that here is A, here is B, and this is my point Z. Yes? And then let us say that, for example, this is C and this is D. And then this point is W. Yes? Now, do you agree with me? So what is this one? So let me call this one X. Let me call this one Y. And then let me call this distance D. Okay? So what is D? D squared is equal to x squared plus y squared. Do you agree? But what is x? X is from here to here minus from here to here. So x is nothing except a minus c squared. Yes? And what is y? Y is from here to here, which is d, minus from here to here, which is b. So it becomes d minus b squared. But because this is even, it doesn't matter if you write d minus b or b minus d. That's exactly the same thing. So d squared is this one. So d becomes equal to square root of a minus c squared plus b minus d squared. And you see this number is exactly the number here. So this distance is equal to this absolute value. So I would write it as a remark. It is important to understand that. So remark. Absolute value of z minus d minus w is the distance between z and w on the complex plane. This is very algebraic to understand, but we can also visualize it as vectors. It is easier. I don't know how much you remember from Math 1C about vectors. So let us say that I will try to draw this picture again. So I will have it here. So this is the real part. This is the imaginary part. And then this is A, this is B. So this is my point Z. And then let us say that here is C, here is D, this is my point W. Okay, from vector point of view, Z can be represented by this vector. Yes? And from vector point of view, W can be represented by this vector. Okay? So I don't know how much you remember from Math 1C. If I ask you what is z minus w as a vector, do you know how to draw it? Probably you have also studied in physics, yes? I give you two vectors, and I ask you to draw the difference vector. To add the vectors, you know what to do, yes? You have a vector here, and then you have another vector here. If you want to add them, so let us say vector v, vector w, you want to add them. What do? You will parallel transport it and put it here. Parallel transport means that you just, as a rigid object, you move it here without changing the direction, without changing the length and anything. And then you start from the starting point and connect it here. this vector that you construct in this way is the sum of two vectors. So you probably remember this. But what about subtraction? Do you remember how we subtract two vectors if they start from the same origin? Yes? Yes, you connect these 2 points together, okay? But if I want to write z minus w, I need to put the tip of the arrow. Either I have to put it here or there. If I want to draw z minus w, I put the tip of the arrow on the z side. Okay, so this is the vector z minus w. Okay, you can also check it, because if you add w to z minus w, you expect to get z, and you really get it. So that is one way to remember it. Okay? If I ask you to add this vector to this vector, according to that rule, you already know this becomes this vector on the one hand. On the other hand, w plus z minus w, w's are cancelled. You are supposed to get z, and you really get z. So that is the correct way. Okay, but now you don't need this algebra at all. Yes? Because the absolute value of z minus w is the length of this vector. Okay? So the length of this vector is the distance from these 2 points. So in any way, however you interpret that, you will get the same result. Okay, so that is very important remark so far. I should have mentioned iz as a remark. It is better to write iz, what happens when you multiply by I. Any questions? Okay, but now there are some questions in the book, so we want to understand them a little bit. So one question is, so let me write it like this. Example, specify the points z on the complex plane such that, so I start with simple one. So number one, they say, for example, imaginary of z is equal to 1. Okay, so I want you to understand, this is a very typical question in this section. Specify the point z on the complex plane such that imaginary of z is equal to 1. What does it mean? It means that you need to imagine the complex number, complex plane, RE imaginary, and then here is yours. You need to specify the points, all the points, I can emphasize all the points z, for which imaginary z is equal to 1. It means that from all these points that are on this complex plane, I am interested in only those for which the imaginary part is 1. For example, let us say that this is 1 unit, this point. Let us say this is 1 unit. Do you think I am interested in this blue dot because of this condition? Yes, because this point, its real part is 0, it doesn't matter. What it matters to me is imaginary point. So the imaginary part of this point is 1. But is this the only point with that property? No, of course not. For example, this point here, the real part is different, but still the imaginary part is 1. I don't know, this point here is the same, this point here the same, this point here the same. So can you visualize what happens if I consider all those points with that property? What it will constitute? Yes? What it be? Are you with me or not? Yes? Do you understand what's going on or not? Hello? So I cannot understand your psychology. Okay, so anyway. So, yes. It's a horizontal line, yes? So I want you to visualize, because there is no way that of course I can tell you what to do, but I am interested in all the points on the complex plane with one condition. The condition is the imaginary part of that complex numbers is 1. All these points are the case, but of course if I just draw them, this is not complete. I hope that you can imagine if I find all of them, it becomes a continuous line, horizontal line passing through the 1. So when I ask you to represent this by some sketching, you just draw this for me, then I accept it. Is that right? Okay, so let us do it another one. So I will do this. I would write, I am interested in all points with these properties, imaginary of z, let us say is greater than or equal to 1, but strictly less than 2. So I want you to understand that they can draw pictures by giving you relations, algebraic relations. So what do you think this inequality, this double inequality, represents on the complex plane? Yes?
Everything between the first horizontal line of 1 and between 2.
Yes, between 1 and 2. So I want the imaginary part be greater than or equal to 1, but it is not allowed to reach 2. So it means that if this number is 2, and this is my limit of 2, I cannot go beyond this line, because if I go above this line, the imaginary becomes bigger than 2. It's not allowed to be bigger than 2. I'm not allowed to go below this line, because in that case, the imaginary part becomes smaller than 1. I'm not allowed to be smaller than 1. But everything between 1 and 2 is acceptable. So this is not a good picture. If you just draw this one, you are indicating 2 straight lines to me. But that is not what we mean. We mean everything in between as well. So I don't know, you have to start coloring things a little bit. Yes. And it is extremely important, this is the convention. Because 2 is not included, you have to show it with dotted lines. So you are just telling me that I drew it in dotted lines because I understand that this 2 is not included. And because 1 is included, you draw it with solid line. So if I ask you what region in the complex plane is represented by this double inequality, this is the picture. Is that right? Is that clear? Okay. So let us solve a little bit different problem. So what do you think about this? Number 3. I would write absolute value of z equals to 1. Again, I have the same story. I am interested in all the points on the complex plane for which absolute value of that complex number is exactly equal to 1. Where are those points? For this problem, you can solve it in 2 different ways, geometrically or algebraically. I want you to learn both of them. Okay, geometrically is much simpler here. So, do you see that? What was the interpretation of absolute value of z?
The distance from the origin to the...
Yes, so this was the distance from z to the origin. I want to have that distance equal to 1. So it means that on the complex plane, this is my origin. I am interested in all points z on the complex plane with one constraint. The absolute value is 1. It means the distance from that point to the origin is 1. How many of those points you can imagine? Infinitely many. Is there any name for these points? The collection of these points?
It's a circle.
It's a circle. It's a circle. When you say it's a circle, you have to specify the center. You have to specify the length of the radius. So what is the center? The origin. What is the radius? 1 length unit. So this is very simple. I cannot, of course, draw it perfectly fine, but this becomes a circle with radius 1. Yes? So if this is 1, 1, minus 1, minus 1. So this represents this circle. Is that right? Okay, might be you get this. You might get this in the exam. Absolute value of z is less than or equal to 1. Then what happens? This time you are interested in all the points with absolute value 1 or less than 1. It means that you are interested in all the points whose distances to the origin is 1 or less than 1. So what happens then? Yes?
It's the same circle, but the inner area is
With the inner area. Okay? So let me just draw it another one if you want to sketch it. So if you want to do this, so you draw this circle, length 1, sorry. And then you have to show that you are actually coloring this region. Because in this case, I am only interested in those points whose distance to this is exactly 1, but here I want 1s, but I also want smaller than 1s, yes? That's the case. Okay. And then this in mathematics is called a disk. It's not a circle. When I say a circle, I exactly mean this curve. But when I say disk, I care about the curve as well as the inside the region. That's called the disk. And because it covers the boundary, it is called a closed disk. This boundary is closing this region. So this is closed disk. But if I give you the same, but this time I give you less than 1, then I ask you to draw this region. What is that region in that case? So this time you have to draw the boundary as dotted line to show me that you understand that these points are not included, yes? And then of course you have to color inside as well. So is that clear? Yes or no? Okay, what about this one? What about number 6? You might see this in the book. They say, for example, 2 less than or equal to absolute value of z less than 3. Okay, I want to wait a little bit for you. Try to understand this. The question is that represent all the points satisfying this double inequality using the experience you got so far. Okay, so what is the result? Yes?
So it's a solid circle centered on the origo with a radius of 2, and then there's another circle that's dotted circle with a radius of 3, and the space between them is shaded.
Yes, is that understandable? Okay, so because you are interested, so if this is the coordinate system, you are interested in all the points whose distance to the origin are 2 or greater than 2, but maximally 3. So it means that, for example, if let us say that this is 1, 2, and this is 3, 2, 3, 1, 2, 3. Okay, I draw the circle with centered origin, but radius 2. So hopefully this is this one. Yes, reasonably good, I would say. Okay, but I will consider this a field circle with solid line, because this is included. But the next one is with radius 3, but that is not included. And then, of course, you have to show that you are respecting these double inequalities, so everything in between is also acceptable. Yes? In mathematics, it is called an annulus. Okay, so that shape is called an annulus. Is that clear? Okay, let me ask you a little bit different question. So number 7, what happens about this? Absolute value of z minus 1 is equal to 1. If I want to find the shape representing this equation, what do you think it will represent? I unfortunately erased the remark. What was the remark I told you? Do you remember? We discussed about z minus w absolute value. What is the interpretation between these two? Yes?
I know, I was gonna add.
Yes.
7.
Yes, yeah, answer 7.
It's a circle, but it's shifted one to the right.
1 to the right. Yes?
Yeah.
With radius,
with radius 1.
center,
Oh, center is it's -1.
no, center should be 1 and 0.
Oh yeah.
Yes, why is that? No, I want you to understand it from this perspective. I told you what is the geometrical interpretation of absolute value of z minus w? The distance between z and w. So this means the distance between z and 1. The distance between z and 1 is supposed to be 1. So the thing that you need to do, you go and draw this coordinate system, the complex plane, real, imaginary. Z is not clear where it is yet, but 1 is clear. Where is 1? 1 is here. Now I am interested in point z whose distance to this fixed point is equal to 1. So it becomes a circle but centered at this point and radius 1. Yes? And as Samir said correctly, this will be this circle. So and then I draw it with solid lines. Yes? So what point is here? If you want to show it, you can say that this is 2. So this is represented by that circle. So is that clear? So what about this one? Number 8, absolute value of z plus I equals to 1. Just let us everyone think. Okay, what's the answer? Anyone else? Which part of it is hard? Yes.
It's a circle with radius 1 and center 0 minus I.
Yes. Why? Because this is not exactly according to my remark. Because in my remark, this distance, the sign between them should be negative. But here, the sign between them is positive. But it is not hard to visualize it like this. I would write it as z. Instead of plus I write minus, but minus I equals to 1. And then I give the role of w to minus I. So this means the distance from z to minus I. Yes? So I will go and draw this. I will find minus I. Where is minus I? The real part of minus y is 0. The imaginary part of minus I is minus 1. So that is the point corresponding to minus I. Yes? And I want all points whose distance to this fixed point is 1 unit. So it means that this is the circle centered here with radius 1. Do you agree? So that is the circle. And if you want here, it becomes minus 2i. So that is the circle. So it is important to visualize it. Okay, let me make it a little bit harder. So what happens, do you think, here? Now, of course, drawing them becomes hard a little bit, but 9, let me put 2 here, absolute value of 2, z, and then let me write plus 2 minus I, and then absolute value equals to, I don't know if I can draw it, but I can explain it for you. Now, for example, 3. Okay, so I want you to visualize this now. Okay, any ideas? Yes?
A circle with radius.
I don't know. But can you explain how you think? Because I don't know what the answer is.
I was thinking
No, because you have a prototype, you have an example, a pattern in mind. The pattern should be like this. Okay? So there should be a minus sign in between, and this coefficient should be 1. Yes, that coefficient should be 1. Okay, so you need to do something so that the left side matches with that pattern. So what do you do? Because you see here, I have a factor of 2. I don't want to have it. I want to get rid of it. So what can I do first?
I was thinking more like the center, how much is the displacement weight?
You can do that, but this is a better way. Okay? But if you want to think, then you have to be very careful about it. Is your guess correct or not? That's what I'm saying. If you want to do it and it is correct, you do it. But the problem is that I always have this interpretation in mind simply, the distance between z and w. If what is given to me is not exactly to this pattern, I try to fix it and make it like this pattern, then I have already my interpretation so that I don't need to be worried if I'm making a mistake or not. So the first thing that you do, I want to get rid of these two. So what do? You can divide by 2, but I want to teach you why, okay? Because we had a rule, do you remember? Absolute value of z times w was equal to what? Absolute value of z, absolute value of w. So you can do it after learning it in one go, but I want to teach you to do it properly. If I want to do this, absolute value of 2z plus 2 minus I, the first thing that I do, I factor a 2 out because my goal is to get rid of this 2 with any price, okay? So I take a 2 out, and then I have z. I divide this by 2, it becomes 1. I divide this by 2, it becomes minus a half I. And then, according to this rule, I can write absolute value of 2, absolute value of the first one, multiplied by the absolute value of the second one. Yes? But absolute value of 2 is 2, so it becomes 2. So you understand that these 2 can be pulled out. But you can do it in one go, but I want you to understand when you pull that 2 out, you are using this theorem. It is not just pulling 2 out from a pair of brackets. So you see, if I give you 2z plus 2 minus I, if you want, without any justifications, you can pull 2 out and simply write this. Yes? But I want you to understand why, even if it is under the absolute value sign, you can do it, because implicitly, without mentioning, you are using this theorem. Okay? Now that you understand, do it in any way that you like. So we divide by 2. Because I pull 2 out, and then because I want to have 1 here as well, I pull 2 out, so I would write it as 2 absolute value of z plus 1 minus 1 over 2I equals to 3. I divide by 2, it becomes 3 over 2. That is one step. It is good because at least I was able to make z with coefficient 1. But what is another problem? The other problem is that I want to have a minus sign between z and the coming number. So my number is absolute value of z plus 1 minus I, 1 over 2I is equal to 3 over 2. Then what do? I would write z. I want to change this to a minus sign, but there is a price to pay. Yes, this becomes minus 1, this becomes plus 1/2 I. And then this becomes 3 over 2. Okay? I'm not saying that this is the best example, but this is the way you need to think, and it is always the case. So then I can interpret the left-hand side as I have here. This is the distance between z and this point. The distance between z and this point should be 3/2. Okay, so that is the circle centered at this point with radius 3/2. I'm not saying that drawing it is easy, but I can visualize it for you, and then we can draw it using GeoGebra probably. So I need to find this point first. The point is minus 1, 1/2. So if I take this one to be minus 1, and this one 1/2, that one 1/2, this is my fixed point. This is this point. And then I put the needle of the compass here and open it as 3/2, and then draw my circle. So I cannot draw it, of course, here. So if you want, so this is 1/2 unit, so 2, and then so for example, because 3/2, this is 1/2, this is 2/2, this is 3/2, yes, and then this is 1/2, this is 2/2, and this is 3/2, for example, and this is 2/2, this is 1 more half, and then 3/2 here. So I don't know, you draw this circle, something like this. Okay? So at least you understand that this represents a circle whose center is this one, and the radius is 3/2. So in the national exam, they can ask you in words. You don't need to draw the picture. So they can say which one of the options represent this. They just explain it in words. One option will be a circle centered at this point with that radius. Then you have to choose that one. Yes? Is that clear? So this idea, this is why I wrote this as a remark, because you will find a lot of examples in the book using this idea. Okay, another type of question, so let me write this one for you and wait for you. So this was number 9. I add this one. Absolute value, this 10 is also important. So I would write absolute value of z minus I is equal to 1 minus z. Okay, so this time I am interested in all the points z so that this is equal to that. I want to wait for you. Okay, did you find the answer? This is a little bit hard question from geometrical point of view. Some of you might be good in geometry, then you can visualize what is happening. But according to my experience, we don't study that much Euclidean geometry in high school in Sweden. So might be you cannot visualize it. So that is a good excuse because this is at the level of your book. It is not harder. This is why I want to use this as an excuse to teach you how you can solve the problem if you cannot visualize it. So you can solve this problem algebraically. Okay, so let me first solve this problem algebraic for you because that is the most natural way to do it. Okay, so if I want to do that, let me write it here. I want to know the points z with that property. Okay, I would say that let z that I am looking for, instead of writing a and b, I would recommend you really write x and y, because in the coordinate system, you are used to use letters x and y rather than a and b. Of course, there is no big difference, but that's my advice to you. Okay, so I would say let this happen. And then I calculate this algebraically and simplify as much as I can to see what happens. Okay? So what happens here, I would say that I put this here. So this becomes absolute value. Instead of z, I put this minus I equals to absolute value of 1 minus z. Yeah, just do it patiently, okay? So I hope that you know, if you want to calculate absolute value of a complex number, that complex number should be written in a standard form. This is not still in a standard form because I see I in 2 places. So this should motivate you in principle to write the real part, but you need to factor the I out. So now it is in a standard form. If I ask you what the real part is, you will tell me x, and what the imaginary part is, y minus 1. Okay, so that's so far so good. On this one, I multiply the minus sign in, so it becomes minus x minus yi. But 1 minus x minus yi, if I want to write it in a standard form, 1 is real, minus x is real, I collect them in one pair, and then I would write minus yi absolute value. So what I did, I assumed that this is the case, I put it in my equation, I try to make them a standard so that I can use the formula for the absolute value. So what's the formula for the absolute value? It's a square root of the real part squared plus the imaginary part squared. Yes? And then equals to the same story here. The real part squared, the imaginary part squared. But you know that I can get rid of this bigger square root signs by raising both sides to power 2. And my goal is to simplify as much as possible, so I will do that. So I get rid of them. So let us do them in one step. I not only get rid of them, but I want to expand these two as well. So x squared, this one squared is the first one squared, 2 times the first one times the second one. On the right hand side, I get rid of this one by raising to power 2 and then expand this. the first one squared minus 2 times the first one times the second one squared, and this is just y squared. And I see what can I simplify? Quite a lot, yes? X squared here and x squared there are gone. Y squared here and y squared there are gone. And even 1 here and 1 there are gone. So what is left is minus 2y equals to minus 2x. Can I simplify more? Yes. I divide by minus 2, and this is y equals to x. And y equals to x is a very famous line, yes? So just draw that. So you just go to the real and imaginary. And y equals to x, you know that this is a straight line whose slope is 1. Yes, so I don't know, and it passes through the origin. Yes, so origin is one of the points. 1 and 1, for example, is another point, because 1, 1 also satisfies here. So I already know that's a line. I know that these are 2 points, so that should be this straight line, which is the angle bisector of the first quadrant. So if I ask you draw something for this, this can be visualized as one straight line. This is algebraic way of solution. But I don't know how much you know geometry. Of course, if you know geometry, you can come up with the conclusion faster. But you have to analyze this geometry. So let me ask you this question. If you can answer this question, then you can also see this from geometrical point of view. If I give you 2 points on this whiteboard, A and B, and then I ask you to find all the points on the whiteboard that are equidistant from A and B. For example, one of those points is what? One of those points, which has equal distances from these 2 points, is exactly the point in the middle. So this point has the same distance to here and that. But that is the only one, or we have more? Yes?
We have the entire straight.
The entire straight line. This one is one of them. For example, this one, the distance from here to here, and these are the same. Higher one, this distance is the same. And also I can also go here. This distance is the same distance. So if you imagine all of them, it becomes a what? A straight line. Yes? This straight line. This straight line is the locus of all points on the plane with the property that the distance from those points to A and B are the same. This is the terminology. The collection of all points sharing one property, that's called the locus of that property. Yes? So, do you remember the name of this? Have you seen the name of this? This is first of all, what is this angle? 90. So it is called perpendicular bisector of line segment AB. So if you are looking for all the points on the plane equidistant to 2 fixed points, that is the perpendicular bisector of those. Now, if you knew this before, then you can solve this much faster and simpler by geometrical interpretation. Why is that? The only thing that you have to do is to do this. I would write z minus I. For the second one, I write it as z minus 1. In the absolute value, it doesn't matter in which order you write it. But what is the meaning of this? I is a fixed point, where? Here. 1 is a fixed point, where? Here. Yes? So you are interested in points z for which the distance to I is equal to distance to 1. So these are playing the role of these fixed points. I am looking for those points. So what is that? The locus is the perpendicular bisector of this line. So if I draw the perpendicular bisector of that line, it becomes exactly that line. So if you can interpret it geometrically and you know the theorems from geometry, it might help you to do that. Yes or no? Okay. But what I expect you at this Math 4 level is doing this. There are questions in the book like this. Understandable? Yes? Okay. There is one question that I want to solve here for you. what happens if I have the same thing, but I want to add a factor of 2 to one side? For example, I have absolute value of z minus I equals to 2 absolute value of 1 minus z. I don't think this is at the level of the book, because in Math 3C, that part teaching you about circles was eliminated. So now I don't think they can ask you these kinds of questions, okay? So this is why I want to write it as an optional, okay? And I want to wait for you to solve it. Or at least you can do some part of it, yes? So the only difference between this problem and the previous problem is that I added a factor of 2. In other words, this time I am interested in all points whose distance to I is 2 times larger than the distance to 1. Okay? Either you can visualize it, that I don't recommend because visualizing it is not easy, or you can do it algebraically. Okay, I want to wait a little bit for you. At least you can start the algebra. Okay? We don't have that much time. Let me start doing it together. So the first part is the same. So I don't want to write it down. So in your solution, you write let this and put them in that equation. The only difference is that you have a factor of 2 here. Yes? So let me start from that part. So I will have a factor of 2 here. So absolute value of x plus y minus 1i is equal to 2 absolute value of 1 minus x minus yi. Yes? Okay, but then the rest of it is more or less the same. So the algebra is not that complicated. Recognizing what shape is at the end is hard for you because you haven't studied that in Math 3C, but they might give you access to GeoGebra to understand that. Okay, so then this becomes exactly as before, x squared plus y minus 1 squared. I have a 2 here, absolute value of 1 minus x squared plus minus y squared. Okay, and then I raise it to power 2. Be careful, this time this doesn't become 2, it becomes 4. So it becomes x squared plus y minus 1 squared is equal to 4 times 1 minus x squared plus this becomes y squared. As before, I expand that. So this is a very simple algebra. So it becomes y squared minus 2y plus 1. I multiply 4 in. Before multiplying, let me expand. 1 minus 2x plus x squared plus y squared. And then I multiply, so it becomes x squared plus y squared minus 2y plus 1 is equal to 4 minus 8x minus 4, so plus 4x squared plus 4y squared. The reason it is not that simple, because this time x squared and y squared are not cancelled totally. So if you don't mind, let me remove them to the other side. It becomes 3x squared plus 3y squared. And then I have minus 8x there. I move minus 2y to the other side. It becomes positive 2y. And then I can move 1 to the other side. It becomes 3. And then nothing is left here, is 0. So might be they ask you the question, because you see here is not hard. You get this one. But recognizing what shape is this, you haven't studied this before, so we can put it in GeoGebra, okay? So what do you expect that it will be? Yeah, so it becomes 3x squared, and then I will have 3y squared, and then I will have minus 8x, and then I will have plus 2y, yeah, plus 2y, plus 3, am I right, equals to 0. That's a circle. Yes? So because that part is eliminated from your course in Math 3C, why this is a circle, it's not a big deal. We can discuss about this. There is no time and no interest probably, but if you want, we can understand why this is a circle. We can also find the center of the circle and the radius of the circle using the algebra. But I think this is a good exercise to combine it with GeoGebra in the national exam. They give you this. Might be they give you this just as an option to choose, or might be they say what is this shape, and then they allow you to use GeoGebra. So you just do this one and then use GeoGebra to see what shape is that. Okay, any questions? Okay, so I will discuss a little bit on this topic next time as well to complete this section. Any questions? Thank you.